Welcome to the Women in AI Research podcast. I'm your host, Ekaterina, and this week I'm at NeurIPS 2025 in San Diego. Hello, could you please introduce yourself?
Hi, my name is Xuechen Zhang, and I'm a final year PhD student at UMass.
Nice. And could you walk us through this amazing work of yours about bridging SFT and RL for reasoning?
Yeah. Today our work is called BRAD, and the motivation is we actually find that the traditional SFT, the RL training pipeline that people normally use, can fail, especially for the small language models. And first of all, we try to analyze why it fails. So, first step is the SFT. We find that the SFT can fail because the expert trace that is written by human or generated by the large model might be too difficult for the small models to learn. And why it's like that? One reason is the expert trace, the expert model is always L times more deeper than the student model. So for just one-time inference, it can do more work than small model. That's the reason why the trace generated by the expert trace is too hard for the student. And that is also true for the human written, a human written trace, it might also be too difficult. And this is also verified by the experiment. We found that this is the base model. And after some supervised fine-tuning with the generate trace, that this one is generated by the Gemini, and this one is generated by the DeepSeek, which is even longer and more complex. It actually hurts the performance. And the more complex the trace is, the more it hurts. So that's the reason why the SFT fails. And then why RL fails, we know that RL needs to try and see. It will generate some rollout, and then we will give the negative rewards or positive rewards to the rollout. But even there's no positive reward, the RL cannot work. And we found that it's always happened when we trying to train the small model. And to solve this problem, our intuition is, okay, we know that currently the task is too hard for small models. So we want to make it easier by doing the curriculum learning. And how we do the curriculum learning by giving different difficulty of the questions. We want to give the hint by control that automatically. And how we give hint? The hint is always partial solutions from the expert trace. And we try to control the length of the hint to control the difficulty. The intuition is the more hint we give the question, then the easier the question will become. And so based on that, we propose our algorithm. First of all, we'll do the regular rollout. And if there are some questions that are too difficult, which means that all the rollout fails, then we'll go into the next step, which is trying to give some hints. Now, how we know that what's the optimal length of the hint, we will control that by this intuition. It's, okay, if all the rollout is success, it means that, okay, the question is too easy. So we want to give the shorter hint. And if all the route fails, it means that, okay, the question is still too hard. Then we want to give a longer hint.
I have a question here. So with the long hint, is it just the longer? Is it just one hint which is long, a long expression of that hint, or it's the sequence of smaller hints, and that's how it is longer?
So actually, you can use different ways to give the hint. But in our experiment, what we do is the hint is always the partial of the solution, which means that because we know that currently people are doing 12 slots, so we will the shorter hint might means that only the first step of this solution, and the longer one might be, okay, I give 5 steps, which give more information.
Yeah. That makes sense. What about the difficulty or easiness of the hint itself? Like one hint could be more important than the other hint. And if you give that more important hint in the beginning, then maybe even that short but more important hint is enough. But if your hints are kind of less relevant to the solution, you can give 3 of them in the beginning, and still it's still difficult for the model to solve.
Yeah, I think that's a great part of BRAD, which means that we don't need to, because we know that, okay, how to control the hint is pretty hard for human. But actually, this one is searched automatically. We use the successful rate of the final rollout to decide, okay, how much hint we truly need. So it's controlled automatically. We don't need to worry about that ourselves.
Oh, that's important.
Yeah, and here's the result. We find that, okay, our method actually have the best accuracy. And also we calculate the computational cost of the whole training pipeline and find that we can actually achieve the good result with the minimum flops. And also we find that the bread can learn from very hard questions, which the normal SFTs and RL pipeline cannot solve. And here are more results. We know that like the SFT can truly work in some setting, which means that, for example, I think the DeepSeek Distill is a pretty good model and they have pretty good results. But we argue that to make this work, we need a lot of data and we need like pretty diverse traits, which is a pretty like hard engineer question. We don't want to do that. So actually, Grad can achieve comparable results with the DeepSeek Distill with much less number of label data. So yes, this is the like sample efficiency of the bread. And also we have some theoretical insight to explain like why the SFT and RL work and why SFT and RL doesn't work and why the bread work.
Nice. Very interesting work and definitely useful for those who are training the small models. By the way, small models in your case, I can see 1.5 billion and 3 billion. Do you see any differences between the across the sizes of the model?
So we found that actually the issue with the SFT and RL fields, it's more serious for smaller models because small models is bigger, it's hard to learn, and also the successful rate at the beginning is lower. Yeah, so we think that okay, the smaller model we target, actually the challenge is more serious.
Right. And do you have any intuition about how generalizable this is across different types of models?
So actually, we think that for different architecture of the base model, it doesn't really matters. So here we show the Q1 results, but actually we also conduct experiments on Llama, which is a totally different model family, and it also works.
So it worked similarly, right?
Yeah.
What about the tasks? Math is obviously about mathematical tasks and mathematical benchmark. What is the GPQA?
It's also a math problems, math task, but like with different like domain, because for math problem there are different difficulty and from different like computation or from the graduate students or from middle school students. So there are different math data sets.
I see. Do you have any intuition on how this could work on non-math tasks?
So I think this can work for all different kinds of the reasoning tasks. The reason why we start with the math is because it's a popular benchmark and it's easy to evaluate how good we are and compare with the other methods.
Right, and it's also probably easier to create those hints.
Yes.
Because it's sufficiently straightforward. Yeah. Okay. Thank you so much, and it's a really nice work. Thank you for your presentation.